Okay, last part for this set of notes, Unit 2, Intro to Chem. We'll be covering C2, the TEACs, C2F, C2G, I6C, and C8C. So, I will collect data and make measurements with accuracy and precision. I will express and manipulate chemical quantities using dimensional analysis, scientific notation, and sig figs. I6C, I will analyze physical and chemical properties of matter such as color, density, and viscosity. And C8C, I will calculate percent composition. Alright, find capital letter E on your notes. And we're talking specifically this time about measurement. And we'll use the metric system or the System International. Or if you're really spiffy, you can say that with a French accent. Okay. So when we talk about measurement, length in the metric system or the System International is the basic unit. The basic unit of length in the metric system is the meter. Okay. So when we talk about any type of length, we're measuring the base unit is meter. We worked on that worksheet last week, and we talked about meter, liter, and gram. So that basic unit of measurement for length would be the meter. And then we add prefixes onto that. So letter A, volume. Volume is actually, you guys all know this, you know the basic equation for the volume of a solid, length times the width times the height. So a volume is kind of like an addendum or something, kind of almost created from the length measurement. So in volume, it's the amount of space something takes up. You guys should already know that definition. The amount of space something takes up. Whenever you see that definition, the word volume automatically pops to your mind. So volume, the amount of space something takes up. The tool that we use for volume, if it's a solid, we're going to use a ruler. If it's a liquid, we're going to use a graduated cylinder. Graduated means that it has little sections. It's got little sections marked off. Kind of like when you graduate, you've gone through first grade, second grade, third grade, fourth grade, fifth grade, all the way up through there. They're graduations. So when we talk about volume, though, we are either going to use a ruler or we're going to use a graduated cylinder. In most cases here, we use a graduated cylinder because we're typically measuring volumes of liquid. If it's a solid, however, we can't always do that. If it's a solid, we can do length times the width times the height, so we have a meter times a meter times a meter, which is a meter cubed. Meter times meter times meter is meter cubed. And if we have a liquid volume, we measure it, the base unit is liters. Now, again, usually we're not going to work with big, massive liters of stuff. We're going to work with milliliters, a smaller amount. A milli, if you remember, milli means 1/1000th. So there are 1,000 little milliliters in a liter. Or another way to say that is, if you take 1 liter and you take 1/1000th of a piece of a liter, that is 1 milliliter. Okay, mass. For measuring mass, we're talking about how much matter is in an object. And we use the digital scales. And our digital scales use the weight to figure out the mass. So basically what it does is it uses the weight, divides by 9.8 meters per second squared, because that's gravity, that's the acceleration due to gravity. And then they calculate the mass from the weight. Our scales are really, really touchy and sensitive. You can blow on them and it'll change. And that third digit to the right of the decimal is never going to stop moving. It's constantly moving. We use the same digital scales that the AP chemistry class does, and they're required to have those scales, so that's why we have such touchy ones. Alright, so mass, how much matters in an object? You should know that definition too. Every single science class you've had has talked about volume and mass and length before. The main tool that we use here is the electronic balance. We also have the triple beam balances or the dialogram balances, which are kind of like the triple beams. Our scales, our digital scales, can only measure up to about 120 grams, so they can't measure heavy stuff at all. The third thing on here that we measure is temperature. We measure temperature a lot, and we don't have to use, thank the Lord, we don't have to use those mercury thermometers or alcohol thermometers, the big long glass thermometers where you had to try and find the little silver line or the little red line and figure out what it was. We have digital probes, so we hook them up to our little handheld vernier probes, our vernier handheld, and we can just read the temperature. It'll just digitally give it to us. So that's a glorious thing. We will not use the Fahrenheit scale. So get beyond it. We're never going to use the English system. We're only using the metric system. So we have the Celsius scale, and the Celsius scale was set up to be based on the boiling point and the freezing point of water. So the freezing point of water is 0. The boiling point of water is 100 degrees Celsius. The other scale, temperature scale that we'll use is the Kelvin scale. And the Kelvin scale is the same basic setup as the Celsius scale, only they took 0 and they moved it all the way down to absolute zero. Absolute zero is the point at which all motion stops. So you guys remember that the atoms and molecules are always in motion? Well, when you get down to 0 degrees Kelvin, everything stops. Okay? And the good thing about this, and the wonderful thing about this, is that the Kelvin scale has no negative numbers, so it won't screw up our calculations later. 0 degrees Kelvin is equal to negative 273 degrees Celsius. So if you have a Celsius temperature, to change it to Kelvin, add 273. Let me say that again. If you have a Celsius temperature, to change it to Kelvin, add 273 degrees. So if it's 23 degrees Celsius, which I think is pretty close to room temperature, add 273. 23 plus 273 is 296. Is that right? That's not right. Yeah, it is. Oh my gosh, it's right. So 23 plus 273, 296, and so you have 296 Kelvin. Children, do not try to do the math in your head. Alright, the next thing we move on to is density. Density is something that you've also talked about in your other science classes, so don't come in here and pretend you've never heard of it before. Density is a ratio. It's not something that you can measure directly. You can't go back and find a tool that measures density. You have to measure two things, the mass and the volume, and then you have to do some calculations to figure out what the density is. So it's the ratio of the mass of an object to its volume. The density of a substance doesn't change with how much stuff you have. So if I have a big chunk of iron, and I find the density of the big chunk of iron, and then I cut a little bitty piece of the iron off and find the density of the little bitty piece of iron, the densities are the same. They don't change. So density is mass divided by volume. And if you'll notice on here, there are three common ways that we have a unit of measurement for density. Typically, we say if it's a liquid, it's grams per milliliter. If it's a solid, we say grams per centimeter cubed, and that's just because we measured the length in centimeters, the width in centimeters, and the depth in centimeters, so we say centimeters cubed. And then we also have a gas, and the gas is weird. It's measured in grams per liter. Okay, and we won't deal with gases until second semester. Now look back at that centimeter cubed and the milliliter cubed. 1 milliliter is exactly equal to 1 centimeter cubed. And if you watch those doctor shows, and they say give them 10 cc's of such and such, cc stands for cubic centimeter. So that cc is also the exact same thing as 1 milliliter. So if they say give them 10 cc's, they're saying give them 10 milliliters of whatever medicine they're talking about. Again, the density, this is huge, that's why it's in big print. The density of a substance doesn't change with how much stuff you have. So no matter how much of the stuff you have, the density is always the same. And that means that you can use the density, if you have this unknown substance, then you can use the density to figure out what it is. So if you have an unknown metal, again, you can use the density to find an identity, to ID the substance. Alright, so here we have a lovely slide here. If you take the same volume of different substances, then they weigh different amounts. So we have wood, we have 1 centimeter cubed, which is just a little bitty cube of it. We have 1 centimeter cubed of water, and we have 1 centimeter cubed of iron. Well, if you have the wood, this wood that in particular they have has a volume of 1 centimeter cubed and a mass of 0.5 grams. So mass divided by volume. What is 0.5 divided by 1? Oh my gosh, it's 0.5 grams per centimeter cubed. Then you look at water. This is when you want to memorize. This is when you have to memorize, children. If you have 1 centimeter cubed of water, it will weigh 1 gram. What's 1 divided by 1? 1 gram per centimeter cubed. Water is the standard. They specifically said, okay, here's the density. This is water. We're going to compare everything to water. All right? And then the third one you have there is iron. If you have 1 centimeter cubed of iron, think of it about like one of those small dice. 1 centimeter cubed of iron is going to weigh 8 grams. So mass divided by volume, 8 grams divided by 1 centimeter cubed, and you get 8 grams per centimeter cubed. So which has the greatest mass and therefore the most dense? The density is the mass per unit volume, so obviously the most dense in this case, all the atoms are really packed in tightly there, would be the iron. Here we have a chart that shows the densities of several different metals. Aluminum is 2.7 grams per centimeter cubed. Brass is 8.5 grams per centimeter cubed. The wood We've got more than just iron, than just metals in here. We have wood, slate, glass, lead, marble, wax. Look at wax, 0.89 grams per centimeter cubed. Does wax float on water? How do you tell if it floats on water? If it's less dense than water, then it'll float. What's the density of water? 1 gram per centimeter cubed. So if it's less than 1, it'll float on water. And if it's greater than 1, it'll sink in the water. Now here we have density of something. It's a solid, but it's not got a nice, neat cube form. And so we have this weird shape, or this irregularly shaped object. And in order to do this, what you do is you see how much water it displaces, or you see how much the volume changes when you put it in. In this case, they've taken some kind of rock, and they're using a graduated cylinder. I really, really, really don't like putting rocks in our nice, pretty glass graduated cylinders, so instead of the cylinders, we'll typically use a Eureka can. Well, I'll show you what that is in class. So you're going to find the mass of the solid on the balance. Always, you're going to find the mass when it's dry. Don't put it wet on the scales back there. You're going to find the mass. That's easy. Just put it on the scales, measure the mass. And then you're going to fill the cylinder with water to a known volume. Let's say you fill it up to 50 milliliters or 50 centimeters cubed. And very gently add the rock to that. And how much does the level rise? In the picture, it goes from 50 centimeters all the way up to 80 centimeters. So how much did the volume go up? 80 minus 50 is 30, so it went up 30 centimeters cubed, or 30 milliliters. So you've got 300, let's say the mass was 360 grams. That's what it says on the picture over here. 360 divided by 30, and that'll go in 12 times. So you have 12 grams per centimeter cubed. That's the density of it. And then here is the lovely Eureka can. With the Eureka can, we fill the can up until there's water coming out the side. We wait until it stops. You don't bump it around or move it around or anything. You wait until it stops coming out the side. And then you're going to get your graduated cylinder, and you're going to hold it under the spout, and you're going to gently put the object in there, and you're going to catch all the water that comes out. And you're going to hold the graduated cylinder up and measure how much liquid came out. And that's the exact same volume as the volume of the thing we put in there. So find the mass of the solid on the balance. Always mass. You just go to the electronic scales and use it there. You're going to add water to the Eureka can until it's just overflowing. Place a graduated cylinder into the spout. Add the object, collect the water, and read off the volume. Once you have the mass and the volume, you can calculate the density. Okay, number 5 here is viscosity. Viscosity refers to how quickly or slowly a liquid flows. It's kind of like a resistant to changing shape. If something's really viscous, it moves really slowly. So think syrup, and think syrup that's been in the fridge for a while. So it's going to move very, very, very slowly. It's very viscous. If something's pretty runny, then it's not very viscous at all. Water, really runny, easy to flow. It's not very viscous. Right. The next thing I have on here is just a little bit of information about graphs. And we have 3 major common types of graphs that we use in the science classes. And they're graphs that you guys are familiar with, but you need to be careful which type of graph you use. And a graph, love graphs because you can just look at it quickly and figure out what's going on. So the first type of graph we have is a line graph. And when you have a line graph, you're comparing 2 things. Okay, you're always comparing 2 things. The x-axis, this is important, will always be the independent variable, or should be, and the y-axis should be the dependent variable. So the x-axis, what is the scientist manipulating or changing? And the y-axis, what are we measuring after that happens? The second type of graph, and this is the one where you guys kind of have to get away from using this too much. Bar graphs are only used to compare stuff when you're counting. You know, in this case, as the graph says, it's birthdays of students by month. So in January, there were 3 students with a birthday in January. There were 4 students with a birthday in February. There were 7 students with a birthday in May. So we're just counting, and that's it. If you're comparing 2 things, you don't use a bar graph. You use a line graph. So bar graphs are pretty limited. The next one is a circle graph. And the circle graph shows how the whole can be broken up into pieces. If they talk about what percent is this and what percent is that, then you know that you're going to be working with a circle graph. And this one's kind of interesting, the average teenager's day. 42% of the time spent sleeping, whether it's in school or at home. 33% of the time in school and 25% of the time other stuff. What do you think? Is that about right for you? Graphs are absolutely useless if you don't have the labels on the graph. It must have a title. If it's got an X and a Y axis, you must label those. You need a key on there. You know, you have to have these things labeled. If you've got numbers on it, you need to tell me what units of measurement those numbers are. It's got to be labeled completely. Oh, and finally, the end of that one, that's the end of the notes for Unit 2.